vivo em 3, 2, 1. Então, tá carregando aqui. Beleza. Bom dia a todos e a todas. Bem-vindos ao terceiro BPT. Eu sou Henrique Ferreira, aqui começando aqui a abertura do evento. Então, gostaria de agradecer a presença da equipe da USP, a presença da equipe da Unicamp, a presença dos jurados de diferentes universidades. Tá? Antes da gente iniciar o primeiro fight propriamente dito, gostaria aí de pedir para que os jurados se apresentem rapidamente. O capitão das equipes se apresente, tá? Então já vou dar a palavra para cada um. E depois eu vou passar a palavra para o chair, o Ricardo, que vai conduzir o nosso Fight 1. Tá? Quando a gente vai começar o Fight 1, a gente vai mudar a língua, né, para o inglês, que vai ser a língua oficial dos fights. Então acho que todos estão cientes, né? E aí, nos intervalos, aí, nessas apresentações, a gente vai fazer em português, tá? Então, mais uma vez, agradecer aqui a presença de todos. Espero que todos tenham aí um excelente BPT, né? E que esse BPT esse ano seja muito divertido e muito proveitoso para todos, tá? Para o telespectador do YouTube que não sabe o que é o BPT, que não sabe o que é o IPT, o BPT é o Brazilian Physics Tournament, então é um torneio de debates científicos de física. Então, alunos de diferentes universidades se reúnem para resolver problemas abertos em física. Então, você que está aí no YouTube, que é aluno, que é professor, que gostaria de levar a competição para a sua universidade, a gente incentiva, então tente entrar em contato com a gente vai incentivar, vai ser muito legal que ano que vem tenham mais universidades participando, mais equipes, né, engajadas aí. E o BPT, pessoal, serve de seletiva nacional para o IPT, o International Physics Tournament. Então, aqui a gente está finalzinho de abril, né? A equipe ganhadora vai, em julho, representar o Brasil no Internacional. Então, a cada ano a gente faz essa seletiva nacional para que a equipe ganhadora vá representar o Brasil no Internacional. Então, sem mais delongas, vou pedir aí para que os jurados aqui presentes, que vão contemplar esses estudantes aqui, se apresentem rapidamente, só fala o nome, a universidade, e aí depois os capitães das equipes também se apresentem, se quiserem falar o nome dos outros integrantes, rapidamente, para que o público fique sabendo com quem eles vão acompanhar aí esse final de semana, ok? Então, é isso, pessoal.
Bom dia a todos, eu sou Cláudio Lencesa, membro aí do jurado, sou professor na Universidade Federal do Rio de Janeiro, trabalho com antimatéria, desejo aí às equipes um ótimo fight, né? E a gente como jurado fica tranquilo aqui, vai se divertir muito, tá?
Eu sou Carol Aguiar, sou professora na UFMG, trabalho com sistemas fortemente correlacionados, também desejo um bom torneio a todo mundo.
Eu sou Lúcio Pereira Neves, trabalho aqui na Universidade Federal de Uberlândia, trabalho com física médica, desejo a todos e todas aí um excelente torneio.
Eu sou o Birajara, sou da UFMG também, trabalho com física biológica e espero que todos tenham aí um ótimo torneio. Boa sorte para vocês.
Eu sou o Danton Vilas Boas, eu sou engenheiro mecânico, trabalho no Instituto de Aeronáutica e Espaço em São José dos Campos, na área de foguetes, desenvolvimento dos foguetes brasileiros.
Eu sou a Daiane, professora da Universidade Federal de Uberlândia, eu trabalho com simulação molecular, simulação de materiais, e desejo a todos aí um bom fight.
Bom dia a todos, eu sou o professor José Serbena, do Departamento de Física da Universidade Federal do Paraná, trabalho com eletrônica orgânica e desejo a todos um ótimo evento.
Bom dia a todos, meu nome é Márcio Daldin, sou professor da Universidade Federal de São Carlos, sou da área de semicondutores e um bom evento a todos.
Agora todos os professores jurados se apresentaram, então o capitão de cada equipe pode falar, podemos começar aqui com a USP, pode ser?
Olá pessoal, bom dia. Eu sou o Lauro e junto comigo, representando o time USP, estão o Bruno e também o Otávio aqui nessa ligação. O pessoal pode estar dizendo um oizinho. Isso. A gente está muito feliz de estar participando aqui pelo terceiro ano e espero que a gente tenha discussões muito frutíferas.
Unicamp?
Bom dia, pessoal. Eu sou o Felipe Mazzi, estou aqui representando o time da Unicamp, junto com a Nelisa, a Maria Carolina, o Anderson, o Leonardo e o João Pedro. É um grande prazer estar aqui mais uma vez e espero que a gente consiga fazer um torneio tão interessante quanto das últimas vezes. Obrigado pela presença de todos.
Então, além das equipes e jurados, temos aqui também membros do comitê. Eu sou o Henrique, eu presido o comitê e faço o intercâmbio com o pessoal do Internacional. A gente tem o Ricardo Guitt. Ricardo, quer se apresentar um pouquinho?
Bom dia, bem-vindos e bem-vindas. Eu sou o Ricardo Gitti, serei o chair, né, o mesário dessa competição aqui, primeiramente nesse primeiro fight, e também estou participando da organização do terceiro BPT.
Professor Antônio, gostaria de falar rapidamente?
Olá, bom dia a todos. Eu sou o professor Antônio, da Federal do ABC. Estou aqui também como coorganização e desejo a todos um ótimo torneio.
Matheus?
Opa, olá, bom dia a todos. Sou o Matheus Pessoa, ex-participante do IPT de 2017 a 2019 com a UFABC e membro do Comitê Executivo do IPT Internacional também. E eu desejo a todos aí uma ótima competição e que a gente aprenda bastante hoje. E amanhã também.
Excelente. Então, pessoal, acho que já fizemos uma boa apresentação aí. Então, vou pedir aí para o Ricardo aí assumir, então, o chair aí, assumir aí o início da competição. Aí, boa sorte a todas as equipes. Esperamos aí um excelente BPT.
Obrigado, Henrique. Boa sorte a todos. Toda vez no início do fight nós anunciaremos quando começaremos oficialmente o fight e mudaremos a língua aí para o inglês, que é a língua da competição. Então, a partir de agora, boa competição a todos. Nós faremos primeiramente o Captain's Fight, que é uma pequena disputa aí entre os capitães da equipe para ver quem começa desafiando quem aí na competição. Welcome to the third Brazilian Physicist Tournament. I please ask to join to the competition the team captains from the team USP and Unicamp, Lauro Barreto and Felipe Mazzi. Can you confirm with the audio that you're ready for the captain's fight?
Yes, team USP is ready.
Yes, Unicamp ready.
All right, so I will share the first captain's fight of the competition. All right, so I'll remember you that the answer must have 4 significant digits, as announced and the rules and the last BPT. So I ask you to use the scientific notation. So one algorithm, a point, another number of significant digits times 10 to, and the power of the order of the number that you want to express. I ask you else to write down the answer and show on the screen, all right? So I can see and take notes to a better way of computing the numbers that you're saying. So for the first captain's fight, we're gonna have a sloth trip to the moon. Imagine now that we are in the future. The humans have already built a space elevator so we can reach moon every time the distance from the moon and the Earth is the shortest as possible. Considering else that sloth starts to climb to the moon in this elevator, and the question is, how long will it take to reach moon surface in a non-stop journey from this sloth? The answer is in seconds, and you have 3 minutes starting now. One minute left. All right, time's up. Please raise your answers. $7.68 times 10 to 9, according to Unicamp, Felipe Mazzi, and 4.5 times 10 to 8, according to USP, Lauro Brás.
That's actually a 9 power. 9 power.
Oh, it's 9.
Yes.
All right.
See, it doesn't close the loop.
4.5 times 10 to 9, 7.68 times 10 to 9. So the answer of the first captain's fight is 7.038 times 10 to the 9. So Unicamp wins this captain's fight. So let's consider now how we answer this question. So the distance between Earth and Moon in its perigee, it's close to 363,000 kilometers, discounting the radius of each of both Earth and Moon. We have a total distance of this trip of 352,000 kilometers approximately. So considering the speed of a sloth as 0.05 meters per second, the time that it will take will be 7 times 10 to 9, which is close to 200,000 years. So better take a ride next time because we don't have this amount of time. Felipe Mazzi, now you are claimed to choose for Unicamp team if you want to oppose first or if you want to report first as positions A or B.
We'd like to oppose first, so B.
Okay, so Felipe and Unicamp team likes to oppose first position B. So USP team will be the first to report, and the Unicamp team will be its opponents, and then we're gonna make the opposite. Unicamp team is going to report. All right, considering the number of problems on the official list to the Brazilian Physicists Tournament is as it follows. I'll share again. Okay, so this year's problem lists include 10 problems of the official list of the International Physicists Tournament. We are going to use the same number of the official competition. So always say problem number 2, 4, 5, 8, 9, 10, 11, 13, 14, or 17. Okay, so now Unicamp team have 1 minute to challenge USP team on the problem they will report starting out. Felipe, please open microphone when you're ready.
We'd like to challenge USP to present problem number 2, pop-up away.
That's a tactical rejection.
Okay, so tactical rejection for the problem number 2. So the first tactical rejection used in this fight, Felipe and Unicamp team, another minute to consider.
We challenge USP to present problem number 9, solar retraction motor.
That's a tactical rejection.
We challenge USP to present problem number 5, distance thunder.
We accept the challenge.
Okay, so challenge accepted to the problem number 5, distant thunder. The USP team will have now some minutes to the preparation of the presentation, and please tell the chair which of the participants will be the reporter of this presentation.
Okay, may I share the screen?
Okay, so Bruno will be the first reporter.
Yes, I will.
All right, so see if you can share screen now.
Can you see?
Yeah.
All right.
ready?
And just a second.
All right.
I'm ready.
Okay, so the USP team, we're gonna be reporting the disintegrated problem number 5 in 10 minutes, starting now.
Hi everyone, my name is Bruno, and now I'm gonna be reporting problem number 5, distant thunder. The statement of the problem is what parameters of thunder can one reconstruct from a photograph of lightning, and how does the answer change if a silent video recording is used instead? Conversely, what parameters of lightning can one reconstruct from an audio recording of thunder? So there are basically 3 parts, and we're going to use the theory developed in the first part to attach in the second to ones. So in order to construct our model, let us look at fused thunder theory. It says that the thunder signal is basically a linear superposition of pressure pulses produced simultaneously by a large number of cylindrical segments connected in series, which compose the lightning as a whole, as you can see in the right. And this theory is, This theory is extremely convenient because no specific energy deposition mechanism is assumed. Then it's all delivered to the shock wave and expanded cylindrically as it performs thermodynamic work on the surrounding atmosphere within a radial distance called relaxation radius that can be easily found from the conservation of energy. The smaller parts of those lightning segments are called acoustic radiators, and they're responsible to emit all the acoustic energy confined. After the relaxation radius, the pulses make a transition to a spherical divergence, which approximately coincides with the transition from the shock to acoustic wave. Brod computed a numerical solution for the pressure pulse and found that this characteristic N-like shape, which is preserved by the resulting acoustic wave. The numerical solution he came up with involves turbulent plasma hydrodynamics parameters that would be very inconvenient and unpractical to use in the model. That's why we'd like to propose a simpler approximated pressure pulse. To do so, we'll neglect the slurring up rarefaction regime of the pulse that corresponds to the region where the concavity points downwards. Both pulses should match at the maximum and minimum, and finally preserve the same concavity. Considering all of that, we propose this piecewise cosine shape, where phi is just the phase. Both the wave number and the angular frequency are already determined by construction. And the initial... Sorry? Oh, okay. And already determined by construction. And the initial phase can be found from the transition process we previously discussed. Based upon the alpha given by Brod's numerical simulation, we were able to compute both the proposal and Brod's pulse energy and estimate that the overall error of this approximated function is 3.7%, which is quite acceptable since as the pulses travel forward, they become even closer and closer. The only problem is that this alpha factor is missing, and one could claim that the pulse's energy should be written in terms of the alpha and the conservation of energy be equal to the total acoustic energy emitted. The problem is that by doing so, we'd also be assuming that the sound spreads uniformly in all directions. And as we'll see later, this is rather inaccurate. So a more precise expression should take into account the distribution factor. And if you consider now in an arbitrary lightning segment, the energy within a certain wedge shell is given by this integral, and in 1974, Phil showed, for instance, that in fact, the energy distribution factor is such that it depends on where you measure the pulse. It needs to be such that 80% of the total energy is within 2 planes tilted by roughly 30 degrees from the center of the acoustic radiator. And our proposal is that this distribution Gaussianly decays with the angle from where you measure the pulse. Furthermore, just to recap, we need to carefully consider the lightning geometry, consisting of a series of connected segments. and each one containing a particular number of smaller segments, which are the acoustic radiators, whose distances to the microphone can be obtained as well. And finally, as a definition of thunder itself suggests, by assuming over all the acoustic radiators pressure pulses from the main lightning channel, we get the final sound of the thunder. Now we'll apply our model to compare the power spectrum of the thunder sound generated by this lightning here with the power spectrum of the sound reconstructed by our model. This was done by considering this reference frame, and from the photograph we were able to estimate the deflection angle from the base of the lightning to the microphone, the distance between them, and also the height of the microphone. These quantities were necessary and sufficient to calculate the scale factor between the pixels of the photograph and the real distances in the area. So besides that, we also assumed the atmosphere as isothermal, leading to an exponential decay in pressure and constancy in the speed of sound. For now, we consider the lightning as two-dimensional, and at last we can only infer the thunder sound from the corresponding part to the thunder lightning captured by the camera. As a result, we've plotted here the averaged power spectrum of the three sounds involved. The blue corresponds to the real sound, the red is the sound reconstructed considering a uniform distribution in the acoustic energy, and the orange is the same but considering the direction bias factor we proposed. As we can see, the power spectrum of the sound with the bias factor was close to the real case. Here, the only difference is that by applying a short-term Fourier transform to the sound function, one can change the dispersion relation by multiplying the amplitude of the eigenfrequencies by this atmospheric absorption coefficient that also redefines the contributions from each of these frequencies into the sound itself. As we can see, both the errors of the power spectra were found from our model were reduced when considering this energy dissipation effect. With a silent video, though, if it's recorded with a high-speed camera and the whole process of lightning formation is captured, one can actually extract information about this three-dimensionality. And if we look at a particular lightning segment, since both y and z velocities of the stepped leaders can be found from the video, one can use the average propagation speed taken from literature to establish a depth relation from each of those segments. Note that as they spread out in the fractal branches, the stepped leaders give the lightning its particular shape. So this means that the depth information would allow us to infer all the distance from all the acoustic radiators, not only in the return stroke, but also in the entire lightning geometry. And as a result, if we use this new lightning geometry data in the previous model, the sound generated would be even more accurate. Conversely, if the thunder sounds given but the distance from the source is unknown, one can set up the experimental apparatus to also detect the echo from the thunder, and as it will have a lower intensity, we can compare with the original incoming sound and finally infer the distance from the source. Since the thunder duration is given, if the speed of sound is known, then the thunder height can also be estimated. In addition to that, the lightning tortuosity can also be inferred from a thunder signal provided through the acoustic direction bias we already mentioned before, in a way that the acoustic radiator more perpendicular to the microphone produces a louder sound because the pulses arrive together, and this is usually referred in the literature as a thunderclap. In that model, sound we analyzed before, the claps are pretty outstanding, as we can see. In conclusion, to answer the questions from the beginning, by making a few pretty reasonable assumptions to link the model to an approachable pressure pulse to the lightning geometry, we were able to successfully reconstruct the sound of the thunder corresponding to the lightning captured in the picture, and from that we obtained a power spectrum that helped us to better visualize how important both the acoustic direction bias and the atmospheric absorption effects are to the resultant thunder sound. The main differences from the silent video were outlined, and as well in the reverse process with the thunder has shown the possibility to apply the direction bias to study the tortuosity too. Also, we'd like to stress that this work takes a step forward in the current literature of thunder, and also the models present new perspectives to better understand the physics behind the connection that these physical phenomena have with one each other. Thank you for hearing me, and I'm open for questions.
All right, so now Unicamp team have 2 minutes for technical questions, and we can start now.
Would you mind moving to slide 5, please? Your choice for this function was it purely mathematical, or is there any physical reasoning behind this shape?
Well, are you asking about the cosine shape?
Yeah, sorry.
Okay, the cosine shape was chosen because it's actually a practical reason. It's easier to take the short-term Fourier transform, but we could use a polynomial approximation, and it would work fine as well.
Okay. On slide 9, you mind, please? You showed a picture which presumably you took online, right? On slide 8.
Yeah, this one was online. Yeah.
How did you get the distance you showed on slide 9 and so on?
Well, we first considered that this lower part here of the picture was cut in about 5 meters ahead of the camera, and with that we also estimated the distance from where the lightning hit the ground with the base of the camera, and using that we established a scale factor between the pixels of the photograph and the real distances.
I'm just wondering, would you just elaborate a little bit more on how you estimated this distance?
This distance here was actually this was taken from well, we compared with other pictures that the distances were none, and that's just an estimation. Like, no, a better estimation would be got with a real video.
All right, so now the opponent team have 3 minutes on its preparation time. Please tell me when it's ready, and also tell us who's gonna be the official opponent. So opponent team, tell when it's ready, and please tell us who's gonna be the opponent.
Felipe will be the opponent. Felipe Mazzi will be the opponent.
Okay, we're ready.
Okay,
Can we share the screen?
Yes.
It tells me that the host disabled participant screen sharing.
And he cannot allow you to put Felipe as host anymore. Clock, please stop the presentation. We're gonna reset when it's ready. That's a timeout for the chairman.
Okay.
Bruno, can you put me as host, because you put as official host, not as co-host. So now you are leading the session.
Okay. You are the chair, so make host.
Yes, please. Okay. Now, Felipe Mazzi, you are as co-host. So try share screen again. Thank you, Bruno. Thank you, co-host now. Okay, if everything's ready, you have 5 minutes starting now.
Sorry, I was muted. Hello everyone, my name is Felipe Mazzi. I'll be the opponent for Unicamp, and we're posing problem number 5, distant thunder. So the problem statement, it's important to restate. It asks if we can, what parameters of thunder we can reconstruct from a photograph of lightning, and how the answer changes if a silent video recording is used instead, and what parameters of lightning we can reconstruct from an audio recording of thunder. So we were highlighting some positive aspects of the presentation. We found that they provided a nice review of the literature on the subject, especially the papers by Arthur Field. A description of thunder as cylindrical pressure waves corresponds to what the state of the art in the literature as well, and provides a good intuition of the underlying mechanism behind the phenomenon. And we found that there are approximations when it comes to the behavior of the spectrum of the thunder, and their approximations for the pressure variation were reasonable. Now, here are some points we are a little bit worried about. First of all, let's say the core of the presentation depends on their ability to reconstruct the parameters of one thunder from a picture of the lightning. The problem is, we found that we were a little bit uneasy that they only did it for one lightning, and the conversion was shown depending on an approximation which was somewhat obscure, because and obviously, since we don't know how different the spectrum from different lightnings may be, so maybe we can't be sure that their model is actually a good match to the physics of the problem, since maybe the variance between different lightnings is smaller than what their model would vary if we change the parameters. So we found that was a weak point. And the fact that only one parameter of lightning was reconstructed, of thunder was reconstructed, was also a bit worrisome, since the spectrum, as I stated, might change in an unpredictable way, given the changes in specific parameters such as distance, temperature, and overall positioning of microphones and cameras. So we would like to answer the discussion by first asking how different are thunder power spectrums. Why wasn't the model applied to more pictures of thunder so that we could get a good, to be safe, that it is an actual description of the system. And we would like to discuss also the approximation of distance that they made in order to get their first comparison between their model and the data. So I'm not sure how much time I have, but that's it. We can follow to the discussion.
Okay, 7-minute discussion.
Sorry, can I begin?
Hi.
Okay, so
okay.
I'd like to begin by asking, I'm sorry, I missed your name. Let's begin by asking Bruno about their choice to show only one thunder and reconstruct it from a lightning.
Okay, first of all, thank you for these pretty valid questions. And this was done due to the lack of experimental data, because usually the parameters that you get from this photograph, the parameters that we needed to use in this photograph were not so easily found. So with this picture here, we knew, like, for example, the features of the camera that was used, and also the place where the picture was taken, and this helped us to use this in the model. So that's why we only focused on this single picture. But we strongly believe that this model would apply to other pictures if the scale factor between the pixels and the real distances could be found as well.
Okay, sure. Do you see the problem that maybe if you don't know how different the sound spectrum, so I may have misread their power spectrum, the sound spectrums of different thunders, if they do not vary too much between them, then there's no way of knowing if your model is just producing a spectrum which is reasonable for most thunders, or if it has any ability to distinguish between the lightning you showed and any other one, right? So it's a single point. It's as if you have a single piece of, you're confirming your model based on a single data point, right? So,
yeah.
What I'd like to ask you is, how do you think the spectrum you obtained or you predicted would change if you change your parameters a little bit, for instance, the distance or?
Okay, this would be we should be worried about this if, for example, we only presented one plot of only one parameter, but we presented 4, and all the 4 plots were really close to the power spectrum, and not just close, but they got closer once we insert the other parameters, such as the atmospheric absorption and the bias factor of the acoustic distribution. So I believe this would be a problem if we only presented only one only one power spectrum reconstructed.
Okay, I'm sorry, maybe I missed it, but the other point is, it wasn't quite clear to us if you were able to reconstruct you do the inverse comparison, right, to get the lightning from the thunder, because we saw many times we saw in the literature that most of these experiments are made by positioning 3 microphones and doing a cross correlation of the signal. Did you try something like that? How did you try, and what did you achieve in terms of reconstructing this lightning geometry?
Yeah, in fact, what has been done in the literature to the current approach to this problem is, in fact, to use an arrange of 3 microphones, and the delay of the sound signal would be used to reconstruct the distances, and then you get the 3-dimensional lightning. But we believe that this, this is true. But if we believe that if if we do that way, we would get out from the statement of the problem, that is from one photograph of lightning. So if we arrange the three cameras, we would get we for sure we would get a pretty more accurate picture. Sorry, we would get a pretty more accurate thunder sound, but we would be using three photographs, and that's not what the problem is asking for.
So is there any, I'm sorry, I missed the final part of your answer, but my impression is that the only parameter you can reconstruct from about the thunder spectrum, sorry, about the thunder is the spectrum, right? You said you did it 4 times.
Yeah, actually we represented only the spectrum because it was easier to visualize how our hypotheses were getting better with the power spectrum. But actually we reconstructed the sound itself, and like the audio, not only the power spectrum. We only presented the power spectrum because it was easy to visualize, but we were able to reconstruct the sound itself.
Okay, and I'm sorry to insist on it, but this on the point of how you were, because you said you lacked experimental data, right? But the experimental data you used, you didn't even have to produce it, right? You just got it from the internet. So presumably you could have done it how many times you wished, as long as you had good enough background data to make approximations. So this is one point in which I'm not sure it's clear why it's a little bit worrying, right? And so once again, what I asked in the beginning, what are there any other parameter you would like to infer from your picture? You would be able to from your model? Because you said reconstructed the audio, right?
Yeah, we reconstructed the audio, and that's sorry, are you asking if we could reconstruct something else?
Yes.
Besides the audio. Yeah, actually, sorry, go ahead.
I mean, from the spectrum, I assume you produce the audio using reverb, and so I figure out time. I think I have a full team discussion right now.
Okay, yeah. Now, from the audio, we reconstructed the power spectrum. That's what happened.
The debate is open for all teams members to participate. Let's go
on. You present a model that considered just one lighting. From your sound, you can tell me what lightning is more branched or not with different lightnings. Assuming that they have the same energy, for example.
So from the sound, are you asking if we could infer whether the lightning is more or less branched?
Yeah.
Okay. Yeah, we could do something like that because with the thunder sound, if you have a higher peak in the pressure signal, this means that the acoustic radiator is more perpendicular in your reference frame and from where the microphone is placed. So and in a smoother signal in the audio means that the acoustic radiator tend to be aligned with the microphone. So this, you could use this fact to infer how spread out the lightning is.
Okay.
I'm sorry, I don't know if I get that, because if the lightning is branched, you have multiple acoustic radiators. You will be receiving multiple acoustic radiator signals at once. So how could you tell which one is branched and separated from a single lightning?
Yeah, you actually can use the fact that the energy per acoustic radiator is well established, and also that you can there's an average number for acoustic radiators, and so from that you can estimate how many acoustic radiators are there in this single clap. So that's that's the key thing.
I like to ask you, Felipe, how would you say that the thunder power spectrum will change from a certain experiment to another? That's related to your question, of course.
Yeah, that's a great question, and one of the key parameters, which is there's actually an analytical expression for it in the literature, is the maximum frequency observed in the spectrum of a thunder, and we know that this is proportional to the total amount of energy in a lightning channel, right? And it varies. I'm pretty sure it's more than linear to the amount of energy. So we might expect that since lightning itself varies in energy a great deal between different occurrences, might expect that at least the peak frequency to change a lot between different data points. So that's why I was worried about having a single spectrum. Right? So I think this is the main feature it would change. And I'd like to, it would be very interesting to see, for instance, just a parametric variation. You take your model and say, okay, I'm going to increase the distance and see how it's affected about what we measure in terms of spectrum. And then I'm going to change some parameters of the lightning and see how that changes my spectrum. And that would be very important, because then we would be able to say, okay, so every lightning is unique. And if you got one right, that means there's a very good likelihood that you made a nice model. But if the spectrum doesn't change quite a lot between variations of the parameter, then that means you have to measure many more in order to get a statistically significant demonstration.
Okay, nice. But to say that you just pointed out something interesting, that is actually the thunders have something in common, don't you think? Which is this spectrum. So do you think there's physics in it? And if there is, so it is fair to analyze those spectrums.
Sorry, in what ways? Yeah.
What?
Go on, Sean. As you said, that they're similar in some way. They're all similar in some way. What did you refer to?
Yes, if they have similarities, so they may be physics in it. Do you think that maybe physics in it? And if there is, don't you think that a theory like Pierce's theory would explain, for example, the density of energy in the radiators, which is really like, according to Bruno's presentation, etc. Don't you think that?
I think I got your question. Could you come? Could you say it again?
Said that the spectrum of some thunders are alike in some ways, and I'm asking you if there is physics behind it.
Yeah, no, that's in principle an open question, but if your model is really able to predict the spectrum, then that's a question that your model could actually answer, right? Because you could just change the parameter and see, okay, now I'm shifting the peak, for instance, towards different directions. I'm not sure how this would happen, because it's a very complicated system, but it would be nice to get it from your model, for instance, since it is able to reconstruct the entire sound spectrum.
Philip, you said something really relevant and important, that the maximum, the peak in the frequency, the maximum intensity in the frequency is what changes the most from one thunder to another. And actually, yes, our model not only matches a similar maximum frequency, but also the rest of the power spectrum. So, I mean, besides predicting a similar maximum frequency, it also predicts similarly the rest of the power spectrum. So that's
I get that you were.
All right, please now it's time for the final remarks of the reporter. 1 minute.
Okay, so just to emphasize that what really matters the most is what really changes from one thunder to the other is the maximum, is the peak in the spectrum, maximum frequency, and our model predicted that, which varies the most from one thunder to the other. And I think another question that I didn't answer from Felipe is how you get the sound from the geometry and not, without using an arrange of 3 microphones, which is the most common in the literature. And we did that by using the definition of thunder itself, because the definition is that the thunder is the sum of all the pressure pulses that leave together the channel. And so we developed an expression for this pressure pulse, and we varied the parameters depending on
okay, so thank you very much, Bruno. Thank you very much. Now we have some minutes of the jury members to ask questions. Jury members, please raise hands and consider question and answer from where who do you want to hear at max 1 minute. So wants to start, please raise your hand. Professor Claudio.
Okay, I have a question, which is the title is distant thunder, and the question is, in one of your slides you show that the distance was about 80 meters. Is that far away enough distance?
Yeah.
And how the distance relates to your analysis?
The distance counters the most on how the shape of the pressure wave changes. So within a certain distance, that's the relaxation radius, the pulse changes its shape a lot. But after this relaxation radius, the N-like shape stays the same. So the distant thunder we interpret as the thunder measured far away from this relaxation radius, which is where the shape of the N-like pulse stays the same.
If I may so complement the question, but you consider the thunder in a sheet, right, as a two-dimensional, does distance plays a role in that?
Yeah, it does, because with a single picture, we can't really infer actually, we could use like machine learning techniques to extract a huge array of different pictures from different thunders, and with an average tortuosity within it, but we weren't able to reproduce that. So in principle, with only one picture, the better we can do is to assume it's two-dimensional, and that's why that's one of the great reasons for the sound doesn't match perfectly, because you see there are many assumptions, and this is I think one of the main ones, that the lighting is two-dimensional.
All right. So Professor Ubirajara.
So I think this question is mainly for Bruno, but I don't know if I get it very right, but I think in the model, you suppose that the sound is created for each segment of the thunder, right? Each cylinder. How do you know, in the model, you are just summing everything, or you are supposing that the sound has a timeline to take the spectrum, like each segment creates that sound, or you have many recorders? How do you know which segment is creating that sound, or if that's important or not, just so I can get a feeling of the model, right?
Yeah, that's pretty interesting. And actually, we assume it feels thunder theory because it's the most convenient for the energy, how the energy spreads out. And in fused thunder theory, that's exactly what I said. Each segment emits a pulse, an acoustic pulse, approximately at the same time, we are assuming that they emit simultaneously because the time delay of the energy passing through the thunder is like 2/3 the speed of light. So that's pretty reasonable to assume it's simultaneously. So the time delay so the thunder duration arrives from the fact that the distances from the lower acoustic radiator to the microphone is shorter than the maximum than the most high from the highest acoustic radiator in the lightning. So this time gap gives us the thunder its duration. Although they go far from the lightning simultaneously. Sorry.
Professor Danto?
I have a question for both reporter and opponent. The question is the following. Is there any limitation or problem in using only one picture or movie to analyze the method?
Yes, there is a problem because the problem is that we can't be really sure if the other part of the spectrum is what really the what the theory is predicting. But this is not so. It's not really a good problem because the maximum frequency, which changes the most, also was correctly predicted by our model. So that's a not so negative point, we believe.
Yeah, I answer, which is precisely what I've been stating from the opposition, is that I'm really worried that if you take a single picture, then it's very unclear. I mean, if you don't know how different the spectrums might be between different pictures, there's no way of telling if your model is just produces a spectrum which is similar to almost any thunder, or if it really reproduces the characteristics of that particular picture. So this is especially worrisome because, I mean, if you could, for instance, verify the correspondence between maximum intensity frequency and energy, there are many things you could do with this model, and I'm a little bit worried that this wasn't shown. So it's very hard to be confident that the model correctly describes the system.
All right, we have a time for an extra question. Any other professor? Okay, so the jury members have 1 minute now to consider their grades. I ask the jury members to put their grades on the link that it was sent to you. All right, Professora Daiane.
Yes.
Have you already sent the grades?
Oh, no, sorry.
No problem. Okay, so Professor Diane is typing their grade right now. So considering the lists of the jury members being professores Márcio Ubirajara, Cláudio, José Serbena, Danton, Carol, Lúcio, and Daiane, the points to the reporter were 8, 6, 8, 9, 7, 7, 9, 7. The points to the opponent team were 9, 7, 8, 10, 8, 8, 9, 9. So now we have some time to remarks from jury members, comments they can tell both teams. Jury member who wants to do this, raise a hand and consider 1 minute. All right, so Professor Serbena.
Okay, thank you very much. I like that both debates and presentations, and I'd like just to stress to the reporter team that I think they miss it in the presentation. Much of the discussion made about the different images and sources that complement their model and to analyze the problem. So they could improve this problem by incorporating the information on the debate into their presentation. Maybe there's a time problem, but I think they can solve this. And the reviewer, I think it was adequate to stress this issue. Okay, just that. Thank you.
Okay, Professor. All right, there was another professor who wants to say anything. Professor Cláudio Lenz.
Yeah, I was very impressed by both the contestants. I think there is an issue from the question that restricts the amount of information you can use, but I think the opponent had a good point as far as the using more than one spectrum. I think it would have been very nice to see the sound wave, to see a slide of the predicted and the actual. It would be nice. I mean, I know time is very short, but it would have been very nice. And I think both didn't. I do believe that maybe distance is a very serious issue on this, and maybe the term distant thunder may apply to not only the shock wave, but maybe to really a long distance, in the sense that this issue of distance of the different segments of the thunder from you are not really in a sheet, in a two-dimensional plane perpendicular to your field of view. But I was very pleased with both contestants.
Thank you, Professor. Professor Ubirajara, I believe you raised your hand.
Yeah, no, but I just want to stress that I enjoy this. So it's not really a question about everything. I think both teams did a very good job explain everything. I was in difficult trying to give notes to you guys, but then I put in the middle to get everything. But now just to congratulate you, both teams. It was very nice discussion.
All right, we have also this time for comments, congratulating the teams. If any other professor wants to tell this, it's the time now as well. Professor Cláudio Lenz again.
Yeah, this was really very nice. I enjoyed. Congratulations. I just have a curiosity outside the question where you could use more information. did you try to use more information on your model? Because it seems like your model is very good, and if you could have used all the information besides what is restricted in the question, maybe you could have got an even better fit. That's just a
Yeah.
curiosity.
Actually we could, and if we could know, for example, how the temperature varies in the atmosphere and the exact pressure profile, the length of the acoustic radiators would vary along the lightning. So this would for sure change a little bit the lightning spectrum. And if we know, for example, what else? How the if we could use, for example, the exact solution for the pressure pulse, that's a numerical solution, and we didn't use because it would be impractical for. But if we had a better computer and more time, for example, the spectrum would be more accurate, and then and that's why we didn't use the exact solution.
Great. Professor Lúcio Neves.
Hi, can you hear me?
Yes.
Okay. I just would like to congratulate you. That's not a very simple problem, but you done it nicely. And the opponent was very polite, raised several nice questions, very important questions. I think you did a great job dealing with the problem. Congratulations. It was very nice to deal with.
Thank you.
Any other professor? Okay, so congratulations to both teams. This was the presentation of USP team on Distant Thunder problem, and our opponent as were the Unicamp team. Now we're gonna have a 5-minute break. So we're going to consider entertaining the YouTube viewers to make a small resume of what happened. So we're going to be back officially at 10:37, okay? So please join me, congratulations both teams from the presentation.
Muito bom, muito bom.
Muito bem, para quem está assistindo a gente via YouTube, essa aqui foi a participação da equipe da USP e da Unicamp apresentando o problema Distant Thunder. A equipe da USP fez a apresentação e a equipe da Unicamp opôs no primeiro round do primeiro fight do terceiro Brazilian Physics Tournament. E essa competição, ela prevê a competição nacional, é uma seletiva para participar do International Physics Tournament de 2021, que será feito de maneira remota. Este ano, a competição ela durará hoje e amanhã, e os dias e outras participações dos fights estão presentes na lista do nosso canal, sendo o segundo fight hoje às 14 horas também. Professores, Matheus, team leaders, se vocês tiverem comentários.
Não, gostei bastante do primeiro fight. Parabéns aí para as duas equipes. Vamos ver o que vai acontecer aí na próxima. Enfim, se vocês tiverem alguma sugestão aí de como melhorar também algum aspecto aí da nossa interação aqui no Zoom, por favor, comente com a gente. Mas se tiver todo mundo feliz, então que ótimo. E vamos continuar aí com o torneio daqui a alguns minutos, né? E boa sorte a todos mais uma vez, mas gostei bastante desse trabalho aí, porque o problema não é um problema tão fácil também de ser resolvido, né? São tantas variáveis. Enfim, muito interessante e animado para ver o que vai acontecer.
Tá certo. Então, para todos que estão assistindo a gente aí e tiverem um pouco perdidos como acontece a competição, ela consiste em uma equipe desafiar a outra numa lista de 10 problemas pré-selecionados pelo o nosso comitê. Nessa oposição, nós temos as etapas de relatar o problema e de opor o problema. Então, uma equipe ela vai mostrar todos os experimentos que foram feitos, qual foi a teoria utilizada e qual foi as conclusões que eles chegaram. E depois, num debate aberto de divulgação científica, será combatido, né, discutido qual foi a melhor solução, o que poderia ser melhorado, quais são os pontos fortes e quais são os pontos que deixaram a desejar do problema e assim elevar o debate da discussão tecnicamente nos conceitos físicos e trazer uma solução compartilhada do problema. Felipe, o que você achou aí da... Tá mudo.
Desculpa, não, na verdade eu ia fazer que o Matheus sugeriu de forma de melhorar a interação do Zoom. Eu só ia pedir se fosse possível, talvez avisar quando fosse para parar e começar a compartilhar a tela. Ficou um pouco bagunçado nisso. Eu fiquei um pouco incerto nessa parte.
Tá certo. Então, o compartilhamento de tela...
Como sugestão, assim, a gente podia deixar as pessoas como co-host, quem for apresentar, porque aí você... por exemplo, que a gente entende também que durante o fight vocês podem querer mostrar os plots, enfim. Então, aí deixando todo mundo como co-host, vocês conseguem se decidir aí entre um e outro, quem apresenta o que em cada hora, entendeu? Então, isso que a gente vai tentar agora para o segundo round, em vez de deixar como host, a gente deixa como co-host, que aí vocês têm essa liberdade de compartilhar a tela, né? Desculpa, Ricardo.
Isso, a gente sempre vai deixar o relator, né, o reporter e o oponente sempre como co-host durante todo o fight, né? Todo round, pelo menos. E aí, na hora, depois que o oponente apresentou o seu slide, que vai ter o debate entre os dois e o debate aberto com todos os membros da equipe, fica aí questão do fair play de pedir e compartilhar a tela, né? Se algo estiver sendo apresentado que não está sendo utilizado, se você quiser tirar da tela, também pode acontecer, né? E aí já deixa livre para o outro já compartilhar, ou então se, dependendo da fluidez das equipes aí, não for algo considerado rude, simplesmente o outro começa a compartilhar e aí já troca as telas e começa o compartilhamento novamente. Assim a gente traz uma certa fluidez aí para a competição.
Legal, obrigado.
Na hora do debate também, as equipes, quando forem fazer o debate aberto, né, para quem está acompanhando a gente, após a apresentação do oponente, tem um debate de 7 minutos entre o relator e o oponente, onde eles vão discutir sobre o problema. Terminado esse período, vai ter um debate aberto com todos os membros das equipes podendo participar e pedir a palavra, né? Como aqui nós estamos uma modalidade remota, não é necessário pedir a palavra em si ou levantar a mão nesse momento, mas você pode simplesmente abrir o microfone e falar e questionar, fazer o que for necessário que você considerar para a discussão, dar a sua contribuição, não tendo a necessidade aí de pedir alguma permissão, já que nós não temos um mediador. Leonardo.
Eu queria fazer uma pergunta sobre a competição. O Felipe, por exemplo, o Felipe opôs agora. Ele poderia apresentar o próximo problema assim, sem nenhum problema ou tem que ser outro membro da equipe?
Na competição oficial, alguém pode subir para o palco 2 vezes, né? Tomar a palavra por 2 vezes durante a competição. Considerando que nós temos apenas 2 equipes competindo, nós não tiramos essa opção, porque senão o número de problemas poderia ficar muito restrito, né? Então, sim, se for necessário, o Felipe pode ser o apresentador da próxima e o Bruno pode ser o oponente da próxima também.
Ah, tá certo, obrigado.
Muito bem, tivemos o tempo do nosso intervalo. Gostaria de saber aí de todos os participantes, vocês já estão online aí para...
Estou sim.
Beleza.
Time USP está pronto.
Unicamp, pronto também.
Ok. Então, para o próximo round, vamos começar aí.
Ricardo, só verifica se
Somente
todos
logo.
os jurados também estão antes de começar.
Tá certo. Membros do júri, por favor, um joinha, câmera, um aceno ou um raise hand já nos indica aí. Danton, Cláudio, Serbena, Daiane. Mirajara. Professora Carol, professor Lúcio Neves. Professor Carol, ok. Professor Lúcio Neves, somente. Não peguei uma confirmação. Márcio também já confirmou. Professor Márcio, ok. Professor Lúcio, o senhor já está presente conosco?
Oi.
Opa, maravilha. Então tá certo. Vamos continuar a competição então. E eu vou abrir para o segundo round do primeiro fight, no primeiro dia da competição do terceiro Brazilian Physicists Tournament. Okay, we're starting now the second round of the first fight of the Brazilian Physics Tournament. The problems list now that USP as the opponent team can challenge the Unicamp as the reporting team, must disconsider the problem number 5, Distant Thunder. Both teams already said they are ready, so USP team, you will have 1 minute to challenge Unicamp team, starting now.
First problem, the second problem pop up away. Accept the challenge.
That's a technical rejection.
Okay, technical rejection for problem number 2, pop up away, pop up away.
Now problem number 13, branching light.
We accept.
Okay, Unicamp have accepted to present problem number 13, branching light. Preparation time starting now.
Sorry, how much time?
5 minutes to preparation time. And just saying who's gonna be the reporter and I'll make you co-host.
I'll be the reporter.
Felipe?
Yes, sorry.
All right. Sorry, I wasn't seeing. Okay. So you can put your presentation, share screen. When you say it's ready, we're gonna start the presentation.
I'm ready.
Okay, so 10 minutes to presentation of the report. Team starting now. Felipe, I believe you're mute.
I'm sorry. Can you restart the time?
Please go on.
When a laser beam, so remind yourself the problem statement. When a laser beam passes through a thin film, random filaments of light are created by an effect known as branch flow. We want to explain the phenomenon and see if you can design a medium to produce specific branching patterns, and also if it can be extended to other wave phenomena. So beginning with a quick review of the literature on the subject, branched flow was observed by the first time in 2001 for a two-dimensional electron gas, and it was observed for the first time in light in 2004, and then again in 2020 in the paper that's mentioned in the official problem statements. In both these cases, a branched flow of light was observed in a soap film, and there's a very complete mathematical description of the phenomenon. As we hope to show you, there's no necessity to restrict the phenomenon to a soap film. And in fact, although this is the most beautiful case of branched flow of light, it is definitely not the only one, and it's probably the least intuitive one. So this is the phenomenon we're interested in. We suspend a soap film with a metal ring, and we shine a laser beam on it. And what we observe is the formation of channels of high intensity. And in order to observe better the phenomenon, we can take the image into the RGB space and take only the green component. So I've selected here a few frames so that you can get a better look at how the geometry of the branching plays out. Okay, let's begin by following the footsteps of the state of the art in the literature, which is the paper published in Nature in 2020. So we begin by considering a slab waveguide, which is a very well-known system in which you have a core with a higher refractive index than the cover and the substrate. And we know that once we solve the Helmholtz equation in this system, we get a dependency between the effective refractive index, which tells you how the wave vector changes for a guided wave, and the normalized frequency, which is a boundary condition term. It depends on the ratio between the thickness of the core and the wavelength. So as you change the wavelength, and in this case, we're only exciting the first mode, we can get different modes to propagate inside the waveguide. Okay, but the soap film is clearly not a uniform slab waveguide, so we have to make a few changes to the usual solution. We propose a separable solution in which you have an XZ dependence and a Y dependence, and the Y dependent frequency function gives you the usual solution with the boundary conditions. And once you take the XZ dependency, you get something that's identical to the time-independent Schrodinger equation with a potential which depends on the difference between the average effective refractive index throughout the soap film and the effective index at the point in which you are interested. So this is clearly not a very intuitive model, and there's no reason why this equation should give you branched flow necessarily. The fact is you need a specific kind of potential. So the potential must be weak enough. That means the deviations from the mean in the effective refractive index must be low enough, and it must be spatially correlated. That means that the correlation length must be larger than the wavelength you're interested in. Okay, but this is, as you can see in the figure, there's no clear correlation between the positions of the potential landscape and the direction in which the flow occurs. What might help give you a better intuition of what's happening here is to think about caustics. So you can understand that the ripples in the potential, which I just described, act like a series of lenses, which if they're disposed with the right statistical properties, you get caustics. So you see that, for instance, when you shine a light on a glass full of water, or when you look at the bottom of a pool. I think this is probably the main everyday experience you have for the formation of channels of high intensity. Okay, so in this picture, how can we shape the medium to produce specific branching patterns? We could make a measurement of the thickness distribution and completely determine the system. Of course, we need only solve the partial differential equation, but this is not feasible at home. So what we can do in practice in this picture is to control general trends. We can tilt the soap film, and we know that when we do that, we get a certain pattern of thin film interference, and we can tell the thickness of the soap film by looking at the color which we observe. So here's a simple experiment. We place a laser in a fixed position, and we get the soap film so that we can tilt it. And we know that when we tilt it, the thickness will increase at the bottom. And as the thickness increases, the effective index increases. So we get a potential gradient pointing downwards in the direction of greater thickness. And as expected, what we observe in the phenomenon, in the experiment, is precisely that. Even though the laser is positioned at the same spot, As we tilt the film from -20 degrees to +20 degrees, we see that what would be our psi wave in the previous slides takes a turn towards the direction of lowest potential. So this is provides good intuition as well. But we want to ask a more fundamental question. Are waveguides really necessary? Because we have seen that non-uniform thickness leads to ripples in the effective refractive index, and that those, if they are arranged with the right statistical properties, we can get lenses which produce caustics. But there's nothing really special about the effective refractive index in this case. We might as well just take ripples in the refractive index for a non-guided wave. And if we can reproduce the statistical properties, we might be able to get lenses and caustics and produce branched flow. So here's a simple experiment. We place Purell, which has a refractive index greater than air, and we position it on a glass plate. So there's no way this is a waveguide. We cannot talk about an effective refractive index, and we don't need to talk about correlation length and the mean refractive index, because this is macroscopic. This is what we call macroscopic branched flow. And here we begin to take the limits. So bear with me. We begin by placing 2 rows of Purell so as to get our first array of lenses. And you might say, okay, this is just refraction. There's no channels of heightened intensity that I couldn't explain with just usual ray optics. But as we continue to add more rows, we can get a clearer formation of branching patterns, such that we can, with very good control, and as we add more and more, we can get more channels. And in principle, we could control this arbitrarily. But okay, this is still a little bit messy. If we want to really emulate a soap film, we can position some droplets and just see branched flow, which we come to a much better approximation of reproducing all the properties of branched flow. And if you take a truly random approach, just by smushing 2 glass plates filled with Purell against one another, we can get something that's essentially indistinguishable from what you could see in a soap film. In a soap film. What's even more interesting, at this scale, can we produce an arbitrary branching pattern? Well, the picture above is something we extract from laser beam shining on a soap film. And in the bottom, we have what we call a coarse manual reconstruction, simply using drops of higher refractive index. So we can emulate the same phenomenon. And what we learned from that is that the underlying mechanism of branched flow is an association of lenses arranged so as to produce caustics. And yes, in a waveguide, you can modulate the effective index by using the thickness variations due to the flow of the soap. But macroscopic branched flow demonstrates the same effect and allows for pattern production, even though you lose some finesse. Even more interesting, and you might be already thinking about that, the phenomenon can be explained in terms of ray optics, given that the correlation length is larger than wavelength. So you have light going through obstacles which have dimensions much greater than its wavelength, so ray optics should be appropriate. And what we can do in this case, and this is highly analogous to what we saw in our previous examples, you can just take a medium with a refractive index which is equal to the mean effective refractive index for a soap film, and you populate it with islands for what you expect in terms of variation of the effective index. And this is inspired by a paper that was published less than a month ago, which is mentioned here. And we can actually do our own simulation. This is a very simplistic simulation. It's just to add the intuition, because we don't add Fresnel coefficients, we don't add total internal reflection, but it does demonstrate that we can, by using a Gaussian distribution of initial angles and initial positions and populating the matrix randomly with islands of effective index, we can produce branching. And in fact, it has been shown in the literature that you can reproduce any property of branched flow just by using a system like this. And of course, I hope I have convinced you that since there's nothing special about confined waves, you can extend it to other medium. All you need is waves flowing through a system where there are ripples in the potential that are small compared to which will obey statistical properties such that the correlation length is more than wavelength. This applies to electron gas traveling through a quantum point contact with impurities in the substrate, or a tsunami wave traveling with uneven bathymetry. So in this case, you have very large wavelengths in the hundreds of kilometers and changes in bathymetry in the order of a few meters. So in conclusions, we have learned that channels of high intensity are produced when a medium acts as an array of lenses capable of producing caustics. This might happen either for thickness variations in a soap film, which modulate effective refractive index changes, but we can also do it in a non-confined region in what we call macroscopic branching flow. We were able to shape the medium by altering the potential so as to change general properties of the pattern. And in macroscopic scales, we position the lenses so as to produce specific branching patterns even more accurately. And finally, of course, the phenomenon has been observed in other wave media. This has been reported widely in the literature, and I believe we have built a good intuition as to why this must be the case. So that's it. Thank you. I'm open for questions. I can see the clock.
2 minutes for technical questions from the opponent team.
Could you go back to the slides in which you present your first analytical model, please?
This one?
Yes. The next one. Also. Okay. Did you perform it and measured any quantified parameter in which you could show us a plot or something like that?
This is the actual solution for the effective index you expect in a subfilm in the range of thickness that I showed you in when you tilt the film. And we get this range by looking at the colors in the thin film interference.
Okay, that's experimental or theoretical?
What do you mean? The graph is
Yeah, yes.
It's theoretical. Yes, it's a standard solution for this lab. Unfortunately, there's no way to measure the thickness distribution at home. It requires some advanced equipment. I'm sorry, I think I can't see the clock. Is this being shown?
Oh, excuse me, I will present. Also, please, could you be the co-host? Thank you. So I think we can begin. I'm not hearing you. Okay, time is. So thank you, Felipe, for your presentation. Thank you for showing us your work. It was a very good presentation, and there are several good points that I noticed in it, and I'm sure that you can clear most of our questions about your work. Okay, so I think we can try to build something together here. Uh, First of all, about the statement of the problem, which is essential, uh, you you presented a proposal of explanation to the phenomenon, and based on the refraction on the pattern in the soap media, and also you showed us in the final of your presentation that you can design a medium to produce specific branching patterns, and we showed us some experiments. You also extended it to other wave phenomena, like the really nice example you showed us with the weather condition in Earth. So, in general, the positive aspects were the reviewing literature, which was really good. Since the beginning of the presentation to the end, you actually contextualized us a lot about it. Also, you presented an intuitive explanation of the phenomenon, which was actually a really good point. Physicists love that, and I also do. You also presented a microscopic view to help us to visualize the phenomena, which is very good. It's very good. And you also showed a good experimental survey, which is also very important in this context. And about that, I also want to understand some more stuff, but only to try to build something still more complete as than it is already. Okay, and it is very good already. First, I would like to understand better the origin of the potential term. You showed us. You said that it was empirical, but I would like to understand understand better the physical motivation of you to using that. Okay, so it's just something to discuss, and also to understand better the relation between the analytical model you presented us in the beginning and the experimental data. You also performed simulations to show us, and if you understood well, you could not reproduce branching in your simulation. So I would like to hear from you why exactly you would say that your simulation could not reproduce those results. Okay, what's the limitation of the actual simulation setups and programs that cannot reproduce exactly this this phenomena? Okay, so far I think we could start talking about a relation with experimental data, and to do that, I think we would need to talk about performing a greater experimental survey and measuring physical constants. Okay, and that's regarding the graph which I call you to come back, that one in blue, which related the refractive index. And in that way, I think we could, for example, change the material you performing the experiment, see, to compare data with your model. See, that's a good thing you could add and still build a still greater argument to your to say that your explanation is a good one. See, so please, if I think we can begin the discussion and talk about that. In order to always, I think it was that those 10 seconds to say that I want here build something. Okay, I'm not. I will never attack you. I just want to with you build something still greater. See, okay, so let's go. So Felipe, thank you for your presentation. I think the first thing it will be great to talk is about the relation between the analytical model and experimental data, which I talked in the last minutes of my speech. So what do you think about the way of trying to compare your model with experimental data points? Do you think that's possible, or there's another way?
Yeah, so first of all, thank you for the comments. I really liked your speech. And that's a great question. Naturally, the next step for solving this problem is to get a real measurement of the entire thickness distribution, which the procedure for that is already outlined in the paper, which I mentioned. And then we can simply solve the PDE with the right initial conditions, and we could actually take a prediction of what the tilt angle, which I showed in the experiment, could be for variations in the potential, right? I think that's what you're asking about in the second point, right? That's about the experiment I did with the tilting. Okay.
Yes.
So yeah, the relation, I showed a general trend because I can't control the thickness distribution here at home. That's important. That's why I took the effort to make microscopic branch flow. I thought this was a single example of shaping was insufficient. So that's actually just a technical limitation. But in theory, I think we'll be able to do this quite rapidly if we had access to the facilities. Can we go to the next point? I mean,
well, I think I can use your answer to motivate another question. We would be, what do you say of changing the material in which you are performing the experiments to several ones in order to compare those angles you're talking about?
Changing the material, you mean to add something?
The media in which the light is reflecting.
Well, there's a very narrow range of materials in which we can see it, right? It must be something which, first of all, it must have an ability to form, let's say, islands of refractive index. So it can't be something like milk, which we tried. It could be any kind of vegetable oil, as I showed, Purell. And so this is you can change the materials in this sense. The soap film is much more beautiful because you get very smooth variations and very tiny variations in the effective index. And that's why I think it's the only example that's mentioned in the literature for branched flow of light. But yes, I would like to try with different materials. Okay, just to mention one point, which I think is important, that raise the origin of the potential term, you mean in the analogy to the time-independent Schrodinger equation, right?
Sorry, what did you say?
When you refer to the potential term, you're talking about the time-independent Schrodinger equation, like the analogous to it.
Yes, exactly.
Yeah, sure. So when you introduce the separable solution, you just produce a separable solution, you plug it into the Helmholtz equation. The y dependency gives you the boundary conditions, and the xz dependency, which is the plane, gives you this equation, and you literally just you sum the average effective index in both the mean effective refractive index in both sides, and you get that potential, which is identical to, which gives you the potential which I showed you, right? So the total energy in the time independent equation would be just the mean. So, and this is the standard shape of what you need in order to observe branch flow. You can write an equation like that for any system, electron gas, tsunami waves, things like that, and all you need, and you will have reliable statistical properties you can infer. Before we run out of time, there's a third point as well, right? You raised it. It was a very good question also.
Yes.
Why can't I reproduce
the simulation you showed us? Though, there are limitations. I mean.
So there are three main limitations. First, the inclusion of Fresnel coefficients, which tells you how much the light actually is reflected or transmitted. Total internal reflection, and the shape. So I used a square matrix, but I really just wanted to show you that I hope you would trust that in the limits we could get to any property. But since it wasn't an original idea, the simulation, it was inspired by a paper published a few months ago. I just wanted to show you that the result exists and that we reproduced it, but I didn't want it to be the focus of the presentation. So, and it will be very demanding in terms of time to perform the simulation like the one which was published. So in terms we can reproduce branching, we just need more advanced models. Maybe more computational power as well. That took a lot of time to process.
But those models, you're saying they already exist? It's just access.
No, the only...
I mean, any software you can just use to simulate that, or you have to be...
Yeah, I did the simulation on Mathematica. So it was really a simple case just to demonstrate the general principle, because I think it's a very nice correspondence, because I showed that the refractive index in the macroscopic realm, let's say, behaves like branched flow. And if you literally treat the effective refractive index as the islands, which I used as the droplets in the glass, you get the same thing, right? So it's a very clear correspondence, and I think it builds an amazing intuition. And so it was...
Yeah.
Without
and I will ask you, would you say that a particulate instead of a continuous media would show a behavior similar to that? Like small crystals, transparent crystals, for example? Would you say that will be observed?
I'll be a bit worried about the interactions of the light with whatever crystals you're using, because I mean, if you use glass, for instance, in principle, glass could demonstrate, if the right conditions are met, it could reproduce branched flow, but because of the transparency, you don't see it. But the key, as you could very well ask, well, why don't I see branched flow all the time? It's because of the statistical properties you need, right? You need something that forms islands, and they need to be spread out randomly enough, but not too many steepness.
Okay.
Too much steepness.
The last thing, I think we can discuss it more. What would you say there are the main maybe lacks of your understanding of the problem? What would you do as a next step?
My next step would be to solve the partial differential equation numerically, but the only reason why we didn't do that is because we can't measure the potential, right? Because we don't have the thickness map. But that's definitely the next step. And even better, I could try to reproduce more branching pattern, right? Because the one which I reproduced was a little bit too coarse, as I mentioned. But I hope I've shown that in the limit it gets finer and finer. But so I could use, for instance, a syringe and place. If you can even do some ray optics and take something you see in a laser in a soap film and always find a corresponding setup in the in the macroscopic realm.
Okay, perfect.
Remember, we are in the open debate time.
Are there any questions?
So, hello. I would like to make an observation, a question. Can your model, you can use your model to calculate the distribution of the branches? I mean, how the angle that the branches form are distributed. So I think you could try to do a scattering problem, so to measure this distribution and try to compare. I think it's a nice way to try to.
You mean scattering to measure the thickness distribution?
No, the angle distribution of the branches. I mean, you shoot a light. Yeah. You shoot a light on a surface that branches the light, and you measure how the angle distributes of this.
Okay, I think you can see that just going to the RGB space and take the green components, it isolates the branches enough. That's a good idea. I'm not sure that shining a light below would probably obfuscate everything, right? So it's because all the experiments are done with the lights off. So because, of course, if you had a better setup, you could. But
it would be a nice, fine setup. But I think it will be interesting. And I'm wondering if your model can predict this distribution in some way.
Well, just to be clear, it's not. given it's a time-independent Schrodinger equation, if you know the Hamiltonian, you know everything, right? So just, and the kinetic energy is given by the equivalent, the analogy to the kinetic energy, and the potential are just if you measure the thickness, you know the Hamiltonian, you know everything. And so
I think that an extension to the Otavio question will be we can see from experiments that the light, when in the soap, it starts very coherent and then it starts to branching. Could we predict that coherence length, that coherence, I mean the characteristic length in which it is coherent still, and then it branches?
Yes, there's a very well-established analytical expression for the position of the first branch. This is well known for branched flow way before it was observed in branched flow of light. It only depends on what's something called potential strength, which is a measure of the statistical distribution of the potential. So it's something like the square root of the fourth power of the variance of the effective index. It's something like that. So I didn't include it in the presentation, first because it's a well-established result, and unfortunately we can't really measure the potential strength, but that's a good point because it's another thing we could improve further, right? If you get to a point where you can measure the thickness distribution, then we could verify this result. It would be very nice.
Mm-hmm. Well, for example, in the publication, I think that that thing could be in your introduction, where you did the literature in survey. You could present that to us. It is something interesting, and it is important to the understanding of this beginning of the problem, right? That it is known already. That parameter is known already. Just
that's why I didn't measure it. I think it would be too unoriginal to show it, but yeah.
I see. As not contextualized in this field, I did not know that. See.
Yeah, it's actually used to predict, for instance, it's useful to predict tsunamis, right? Because the bathymetry of you have a 200 kilometer wavelength, and you have variations in the bathymetry which are much similar to the thickness variations in the soap. So branched flow is,
I think.
Yeah.
Yeah, thank you. I think that
Bruno's got his hand up,
right?
Can I ask?
Sure.
Maybe anyone from Unicamp had questions. Maybe it will be interesting to hear from them. No? Well, otherwise, Bruno, you can follow.
Okay, Felipe, congratulations for the experiment and the presentation. And I would like to ask about something that there is in the Nature paper. They trace a relation between the distance from where the light goes and the number of branches. Have you tried to do this? There's a plot relating the number of branches and the distance from the source.
The distance to the first branch and the number of branches.
Yeah.
Well, I'm sure the thing with this problem is, since everything is determined, once you know the potential, in principle, you could do that. I think I don't have an intuition as to how these two properties would be related, actually. But we know that if the distance to the first branch is greater, that means that the term they call potential strength is smaller. So there are less smooth variations in the potential. So that might be. I don't want to put my hand. I wouldn't bet on it, but there might be something there.
Yeah, thank you. Last message. I really enjoyed this discussion. Thank you.
Me as well. Thank you.
Okay, thank you very much. Now, 1 minute for reporter's final remark.
Sorry, do I have to? Okay, sorry. Okay, so I believe I don't have to share my screen. So I think we had a very productive discussion. The opponent team seemed to agree with most of our considerations, and they introduced many interesting ideas, which would definitely help us to make more experiments in the future, and especially when it comes to actually predicting for instance, the way in which we chose to shape the medium, right? So we could, the idea of actually measuring the thickness distribution and predicting the tilt angle and comparing. And so there's this point, and there's a second point about the position of the first branch, right? So these are 2 points which were raised in the opponent's speech, which we'll definitely look into it in the future. And I think it was a very nice discussion, so thank you.
Okay, so now 9 minutes for questions from the jury. Jury members raise hands. Professor Serbena.
Okay, thank you. I would like to ask about specifically the sound waves, because in the statement of the problem, it's explicit there. So I would like you to comment something on specifically on sound waves.
It's a great question. Sound waves are a little bit harder to. So what would be the analogy to the potential in the case of sound waves, right? You need to have a medium in which the wave is encountering boundaries in which it has to, one, obey boundary conditions, and second, change its speed, right? And those 2 things will cause it to refract. In the case of sound waves, we would need a medium, probably density variations, which change sound speed or temperature. Well, actually, these 2 are coupled, right? So we need a medium in which we could modulate changes in the speed of sound with the right statistical properties. This is obviously, I think, much harder than water waves or light. So I'm not sure this answers your questions experimentally, but the principle is this, right? You'd have to provide this kind of ripples in the potential in the speed of sound.
Okay, thank you.
Professor Claudio Lenz.
Okay, it was very nice that you showed that you can do this with ray optics. And that opens a possibility that I get, like, for instance, plexiglass, acrylic cylinders, cut them and put on a table, and then come with my laser and see the pattern, for instance. And my question is, have you considered that, and to which precision you would need to point your laser and to localize the cylinders, so that the actual geometric distribution of the branching could be fit to the model? My question then is, have you considered, what kind of uncertainty or precision you would need to actually fit the model?
Yeah, so thank you for the question. Are you laying the cylinders flat on the surface? Is that what you mean?
No, the cylinders go up, right? So you have a surface and you have many cylinders up.
Oh, okay.
So,
okay.
And then because it's, it's just one dimension that I want, it's just a 2-dimensional, right, plane. Mm-hmm. And then I shine the laser, right?
Yeah, this is somewhat analogous to the example I showed with the droplet, right? So this
right, exactly. But in a simpler geometry, because you get a cylinder, right? So you only have, right?
That's true, yeah. It takes away the uncertainty of having the height of the thickness of the droplet, right? Exactly. That's a very good idea. In principle, let's say the finesse of how well we can reproduce the branching would depend solely on the statistical properties of the cylinder's position, right? So if you take the ideal as being the soap film, you can approximate it indefinitely, right? So you could take smaller and smaller cylinders and place them like the thickness variations are placed in a soap film. So the short answer is, well, you just have to use the known results for branched flow in the statistical requirements, and you can try to reproduce it to the cylinder. But in order to get a perfect correspondence, you'd have to have something on the same magnitude, which would be, let's say, microscopic branched flow, right? So, let's see.
Okay, can I just add, because you're always talking about statistical averages and so on and so forth, and distribution, but the question is, could you try to simulate, and I'm sure you can, because you mentioned the ray optics example, to simulate a single case. So
okay, I think
it's got to be deterministic when you have specific directions and so on, that you get some sort of single distribution, right?
Yeah, sure. You could make a one-to-one correspondence.
Yeah, and it's a question that relates to another question, which is the Schrödinger equation. You said you can find the energy eigenstates from that Schrödinger equation, right? But you should be able to find the wave solutions as well. So can have you tried to plot the wave solutions from that equation?
The only reason I didn't is because I don't have the potential, right, to input it in the equation. In principle, if you know that, you could simulate it numerically, and you're right. Then you could solve it as expected. You could get it completely determine the system just by measuring the potential. And the point about ray optics, just completely, yes, you could make it. You can even build an algorithm that takes an image and uses ray optics to reverse engineer it and choose the positions of the cylinders that you mentioned.
Okay, Professor Birajara.
Thank you, Felipe and everybody. It's very nice to be here. If I got it right, in the end, you get a parameter that is the correlation length that should be bigger than the wavelength, and then you can compare in different waves, right?
Yeah, right.
Okay, so in the soap bubble, you have a very thin film, like you show in a beautiful experiment there. I like it very much. But then the thickness is smaller than the wavelength. And how then in the structures is smaller than the wavelength, you can compare what is the important parameter to tell me what is the correlation length in that case, for example, in the wave bubble.
Good. So if I tilt the soap film too much, then the trend of greater thickness towards the bottom overrides the fluctuations. So in this case, I would have too little correlation length, and then you don't see the phenomenon, right? So that's why I only put from -20 to 20. And you can see that as you increase the angle, the branching gets narrower and narrower. So yeah, the parameter, I'm not sure if that answers your question, but that's the limit, right? So you can't let the general trend kill your ripples.
Good. It's just like because you are talking about structures smaller than the wavelength, right? The thickness of the, and then you must have a correlation length bigger. Then you told me that, so it's the fluctuations. The fluctuations are still smaller than the wavelength, right? Or no? I don't know. I don't know about the problem. I just want to get a feeling.
Yes, it needs to be important that what matters is not the thickness itself, it's the effective index that corresponds to the thickness. So what happens, the correlation length is the measurement of the size of the islands that you see in terms of effective potential, right? So that's what needs to be greater than wavelength. And what you see and what you get in the literature is that on average, these islands are in the range of a few millimeters, tenths of millimeters, while the wavelength is nanometers.
Okay, great.
Okay, we have time for a last question. Professor Claudio?
This is a question for the opponent. You asked many times about the potential, the origin of the potential term in the Schrödinger equation. And now that it's been clarified, that's just the index of refraction, right? Could you propose a method that the reporter, the other team, can actually perform an experiment and put it against the model? Because index of refractions, if you can do with ray optics, they are well determined. So can you propose something for the
maybe following your idea of using that ordered system with the cylinders, he could computationally describe a potential to each cylinder in which it would describe that a particular media and an effective potential for the other media in which the cylinders are inserted. So maybe he could use this methodology using his effective idea to extend to your proposal, Professor. Does it make sense? Using that discrete thing?
Yeah. Okay. Does Felipe want to comment?
Well, I'm not sure I understood it completely, actually, to be honest. But
the question is whether you could quantify.
No, I got the question, and the answer I'm not sure, but quantify the, sorry?
If you use material of known indexes in this discrete system, whether you could build a system that you can quantify and actually predict the model, and actually run your model.
Yeah, I think even the setup I showed with the Purell might be suitable for that, right? So you could measure it with more precision. I actually put graph paper behind the glass so I could see where I was putting the bubbles. And the dream scenario would be I can find coordinates and radii and produce linear branching patterns. And that would be the ideal gold standard.
Okay, thank you for all jury members that participated. Now, I asked you, all jury members, to set the grades, consider it, and put it on the official link. You have 1 minute to Okay, so I'm confirming the grades of professors Márcio Ubirajara, José Serbena, Carol Aguiar, Danton. We still have professors Daiane, Cláudio, and Lúcio. To insert their grades. Let me reload the page. You see that there's a problem. Okay, now I see it. So, if you give me some minutes, there will be also the results of this fight. Okay, so grades considering round 2. Professors Carol, Cláudio, Daiane, Danton, José, Lúcio, Márcio, and Ubirajara. Round 2 was Unicamp reported team 9, 9, 10, 8, 9, 10, 10, 8. For the opponent team, USP, 9, 7, 7, 9, 8, 8, 9, 8. Remarks from the jury now. Any comments? Anything you can congratulate the teams or add-ons? Professor Serbena, please.
Okay, thank you. I would like to congratulate both teams. I especially like it that you presented, the reporter team presented a model, although a simple model, and experimental results. So I think this is a nice approach. Of course, it depends on the problem, but I think the teams should always look for this approach. And concerning the opponent team, I think that in my opinion, the limitations of the model were best discussed by the reporter team. So, but however, the 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 points were very well discussed by you. Only this only this single issue. Okay, so congratulate you both teams.
Okay, Professor Lúcio Neves.
Hello. I would like to say that both teams were very good. I would like to say also that Mr. Felipe Mazzi has a very good English knowledge. It's very easy to understand what he says. That's very good for the discussion. Congratulations. I also would like to emphasize that this presentation from the reporter group was well done. Well, they really took care with the analytical analysis and making the model. The experimentation was nicely done. It's an experiment that could be done at home, so with cheap materials. That's very interesting. I like when people do those kind of stuff. And I also like to say that the last slide from Mr. Felipe Mazzi, he presented all the team, and I think that's very good when you see you are dealing with the team. So it's very good when the presenter puts everybody there and show that everybody worked together. And there are also some girls there working. And I have a project, Girls on Physics. So I like when you have this mixture of people. This is very important for me. When you have a team with a lot of girls working together, we need that. So this has nothing to do with physics, but I am a he for she defender. So I like when I see those things. Congratulations for both of you.
Okay, Professor Cláudio Lenz.
Well, I would like to join my colleagues in congratulating both teams. I was very pleased with the reporter experimenting, the many experiments he showed, and the fact that he expanded to go beyond the Helmholtz equation, the effective Schrödinger equation, to other phenomena, even to ray optics, showing that one could, perform this classically, right? Essentially. And for the opponent team, I think they have an important point, which is this comparison between a single realization actually fitting not just the qualitatively the phenomena, seeing the phenomena qualitatively, but also doing a quantified comparison between experiment and data. And so congratulations. I think the reporting group could try to solve that equation for supposing values. I mean, you can suppose values from the literature in a specific situation and show the result of that Schrödinger equation for assuming a certain value of the index of refraction that you would obtain. But congratulations to both teams. Very nice. This phenomenon is really beautiful. I don't know if it has implication in sound waves for petroleum exploration, for instance, it's a questions on, how this plays in other fields. Maybe not people drew this inverse study of the echo from the blast, and I don't know if this kind of phenomena plays a role in that exploration, for instance. Congratulations. Thanks.
All right. Thank you very much, professors. Please, everybody, join me congratulating both teams for the presentation. So this is the end of the round 2 of the first fight of the 3rd Brazilian Physicists Tournament. Thank you for both teams. Muito obrigado a todos pela participação. Para vocês que estão nos assistindo, nós estamos no final do primeiro fight da competição do 3º Brazilian Physicists Tournament. As equipes da USP e da Unicamp se enfrentarão aí em outros 3 fights que acontecerão hoje ainda às 14 horas, através deste mesmo canal, e outros 2 amanhã, sendo a grande final, sendo o primeiro às 9 da manhã e a grande final às 14 horas. Agradeço a participação de todos aqui, os presentes, agradeço a participação do comitê que tem nos ajudado, o professor Antônio Neves, o Matheus, o Henrique Ferreira. Quem tiver comentários aí, fiquem à vontade.
Agradecer a presença aí de todos e comentar para quem está assistindo a gente. Eu vou colocar o link aqui do próximo fight, que vai acontecer às 14 horas. Então, quem está acompanhando pelo YouTube vai receber aí o link, tá? A gente tem um fight hoje às 14, o segundo fight, amanhã às 9, o terceiro fight, e a final amanhã às 14. Tudo bem?
Beleza. Tradicionalmente, os jurados da competição, eles não têm acesso às notas das equipes, então eu gostaria de pedir que os jurados saíssem da sala, porque a gente vai comentar as notas e divulgá-las para o pessoal que está nos assistindo. Tudo bem? Beleza. Então, comentando a respeito das notas agora após o final do primeiro fight. Compartilharia a tela aqui com vocês. Nós tivemos aí pontuação final da USP 40.2. Lembrando que a pontuação de cada fight é possível chegar a um score entre 0 e 50. E a Unicamp, campeã desse primeiro fight, 45.4, tendo aí um bônus por ter ganhado um fight, chegando com final score aí para ser somado à pontuação da competição de 47.67. Então, parabéns a ambos os times.
Tem um segundo? Posso? Eu só queria agradecer, porque para mim as discussões foram muito interessantes. Eu particularmente amo falar de física, então para mim isso aqui foi gostoso e agradeço aí o time da Unicamp por apresentar o trabalho deles. Foi realmente muito legal. Para a gente também foi ótimo apresentar o que a gente fez e poder construir alguma coisa juntos, né?
Ótimo, obrigado, Lauro. Também queria agradecer a organização e os jurados saíram, mas eles também. E foi ótimo, adorei a discussão. Só Ah, não, tá certo, tá certo. Obrigado. Então vejo vocês às 2, né?
Isso, pessoal. Agradeço aí a participação de todos. Peço perdão por conta a respeito dos jurados. A gente não tinha questionado nem discutido isso aos demais membros, né? Geralmente, as notas no IPT, elas saem num formulário à parte e os jurados não as sabem logo após o final da discussão. Então, a gente pode até comentar isso, discutir isso para as próximas, né? Eu acabei tomando essa decisão aí para suprir aí a vontade da galera do YouTube e também das equipes que estão nos acompanhando, a ansiedade de saber as notas. Muito obrigado pela participação de todos. Como o Lauro falou, não tem um jeito melhor de passar o sábado do que ficar discutindo física. Então, nos vemos novamente às 2 horas da tarde nesse mesmo canal para o segundo fight do terceiro Brazilian Physicists Tournament. Muito obrigado a todos. Tenham um bom dia.
Obrigado.
Obrigado, até mais, gente.
Obrigado.
É nóis.
Até mais.
Valeu, até, pessoal.
Valeu.